So hello, this is our second lecture, and today we're going to continue our crash course in the basics of Python needed for data science and machine learning. So on my screen, I have 4 different notebooks covering 4 different topics that are important to know about. The first one might seem a little maybe esoteric, but trust me, it's important, especially when we get to using other people's code, other libraries such as scikit-learn or TensorFlow. Because when we go and look at the source code, everything is written, not everything, but a lot of things are written in the form of classes, Python classes. Okay, so as I mentioned last lecture, everything in Python is an object, and objects have attributes and methods. But what does this really mean? This means that, well, I guess the best way to illustrate this is by just giving you an example. And just in case I'm picking up too much sound, be sure to mute your mics unless you're going to speak. All right, so here's the problem setup. Suppose that we are dealing with polynomial functions, right? These are functions of the form p of x equals to coefficient times x to the power n plus another coefficient times x to the power n minus 1, all the way down to a last term, a0 here. Okay, so these are just polynomial functions, and we happen to be dealing with them all the time. So in order to handle these functions from a programming perspective, handle these objects from a programming perspective, we decide to create a custom representation, a way that we can deal with these objects with Python. Okay. Now, one natural way to represent a polynomial of degree n, recall that the degree is the highest power of the polynomial, is with a simple Python list. So for example, if p of x is equal to 2x cubed minus 3x plus 1, this is a degree 3 polynomial, and we can represent it as such. So what's going on here? So this Python list has a 2 here, 0, minus 3, 1. So one way of thinking about this is 2 times x to the power 3, and then plus 0 times x to the power 2, plus minus 3 times x to the power 1, and then plus 1 times x to the power 0. Okay, so that's what I mean by representing this polynomial by this list. It seems to me that this is one way that we can do that. Okay, so let's just go ahead and copy this code and paste it right here. Run it. Okay, so maybe what I'll do is I'll print the degree of this thing. So this functionality that I'm demonstrating right here inside of the F string is something that is new to Python 3.8 and higher. So we see that this polynomial here has degree 3. So this representation is storing some information about the polynomial. We can find the length of it minus 1, that'll give us the degree. And then inside of this list, those are the coefficients of the x variables, right? So this is one way of doing it. But it's not satisfactory, because it's like, if we want to get the degree, we have to write this every single time. And we might be dealing with many different polynomial objects. So what we can do is now represent these polynomial objects as a custom Python class. Okay. Python classes give users the ability to group data and functions into a single customized type. So let me just repeat that one more time. Python classes store data and functions. Okay, so the data is what we would call a class instance attribute, whereas the functions are what we would call class methods. And in the previous lecture, you might have heard me say method over and over again, right? These are the same methods that I'm mentioning here. So this is how we create a class object in Python. So class is how we say that we're about to start making our class. Then we give our class a name, typically with a capital letter, polynomial, and this is an object, colon, and then white space to indicate they're inside the class definition. Now, what's going on in here? This first method here is a Dunder method, or a double underscore method. There are two underscores here, and then init, two underscores, and then we enter into the function. So this is a special method in Python, and I'm going to provide a list or a link to a list of all the Dunder methods that are available when creating custom classes. This one is pretty much used anytime you create a custom class because it's initializing the given instance of the object. So we'll understand a little bit more about that in a second. But just think of it like this. We're creating a general container of data and functions that we want to apply to different instances. So it's convention that when you're inside of the definition of a class, to call the instance in question self. Okay, you can call it whatever you want, but I'm going to call it self to stay with convention. So this is just referencing the self. It's the instance that we're looking at. And then we're passing in something called coefficient or coef. And there's a typo here, actually. This should be 1f. Okay. So then inside of this function, this Dunder method, this init method, I say that self, which is the instance in question, dot coefficient, is equal to what we pass in, coefficient. And actually, another typo here. Right? So all this is doing, and actually I'll just show you real fast to kind of illustrate what's going on here. So I just copy that and paste it right there. And then I'm going to, actually, I don't have to do that. So I can just say, okay, there. This is a simple definition of a class, and this is the init method. So then I can say, after I've defined it, I can say p is equal to polynomial, and then I'm going to pass in some coefficients. So for example, 2, 0, -3, 1, like that. Okay, I'm going to put in another cell underneath here. So do that. So now, if I look at the definition here, so self is p, for example. Okay. If I wanted to make another instance, I could say q is equal to a polynomial class. And maybe we want like x squared minus 1. So what would that be? 1, 0, minus 1. So this would be 1 times x squared plus 0 times x minus 1. So these are two different instances of polynomials. Okay? Now, again, in this first line here with p, p is acting like self in the definition. Q is acting like self in this definition. So self is referencing the instance of the object. And if we want to get this information out of the object, we just use that dot notation. So p dot coef, those are the coefficients of p. If I do q dot coef, those are the coefficients of q. So whenever you see self dot something without parentheses, this is going to be a way of containing or storing data for a given instance of an object. So when I create this polynomial, it's storing this as data. When I make this q polynomial, it's storing this as data. And the way that we access that data, or to be more formal, the attribute called coefficient, we call dot and then the name of the attribute. So again, in the definition of a Python class, we have these classes group data and functions, right? So we have data coefficient, right? The next bit here is a function that we're going to define inside this class, right? So we have an attribute, now we're going to define a method or a function, okay? So def degree, this is going to be the degree of the polynomial. We have to reference self, which is the given instance of the object. And then this is the function to find the degree. It's just the number of items and coefficients minus 1. And again, I can access those items and coefficient by calling self.coef. So this is accessing the data that's contained in this polynomial instance, and I'm getting the length of that coefficient list, and I'm subtracting 1, and then I'm returning degree. So now, if I add this to my definition down here, so of my polynomial, I can say def degree. It doesn't take any arguments, it just takes itself. And then we can say degree is equal to the length of self.cof minus 1, and then return degree. Okay. So now if I exit out of that, by exiting out of the white space, I press Shift Enter. Now, not only do P and Q have data as coefficients, but they also have degree. And I can access that with the .degree method. The degree of Q would be 2. And that's, again, these would be the coefficients of x squared minus 1. If I look at the degree of P, it'd be 3, right? And that was this guy here, this degree 3. So
I have a question.
Yes.
So if for the right where you have that highlighted, if you didn't put -1, what would happen?
It would give you this number of items. It would give you 4 instead of 3.
Okay.
But the last term in this list is there's no x there, right? This is just, right? So the x's start here. The powers of x start there. So that's why we subtract 1 off. Okay. So again, this is just illustrating how to create like another instance of it. We just copy that, paste. We see that if we try to print out Q, this is what we get out. It is a type polynomial object. These are its coefficients. And then this is its degree. And if you want a nice little equal sign, you can just do that inside of the curly braces and you'll see this pop out. Okay. So far, this class that we've made, this polynomial class, it's sort of working, right? It tells us the degree and it tells us the coefficient, but it's not especially useful right now, right? We might want to print it out a little bit nicer as well, right? Like, yeah, we can kind of infer that this is 2x squared minus 1, but we have to think about it. It would be nice if we could print out a nice string, like maybe we could make a class method called string or something that if we call that method, it shows us what it looks like. So this code here is kind of giving you a hint on how to do that. So this is our polynomial, and this is what it should look like. It should look something close to that, right? So here, I'm basically giving you a hint as to how to build this string. So I say degree is equal to the polynomial degree by referencing the degree method. And I call this thing called p string is equal to an empty string. It's just, there's nothing there. And then for I, comma, a, and enumerate, which you should know what enumerate is from a previous lecture. So enumerate, just if you don't recall, it's finding the index together with the value inside of this list. Okay. So then I'm going to plus equals or add on to this empty string the following. A, which comes from coefficient, times x to the power the degree minus I. Right, so let's see what happens when we run this. Okay. So maybe I should put in a space here. So this is P, these are the coefficients, and this is what we've printed out. Okay. This looks correct, 2 times x to the power 3, and then 0 times x to the power 2. And then we have minus 3x to the power 1, and then 1 times x to the power 0. That's close, but we need to put in some plus signs. It's not perfect. So what we're going to do is basically the same thing, except for now, we're going to add a little plus at the end. Okay. So let me just copy this now, paste. So same exact thing, just now we're doing a plus, and then we have a print something going on here. So that looks a little bit better, right? Now we have the pluses in between them. So it's 2x cubed plus 0 x squared minus 3x plus 1 times x to the power 0. You might be wondering why I'm doing a minus 2 here. Well, look what happens if I get rid of that minus 2. I have this trailing plus sign here in a white space, right? So the way that I get rid of that is by slicing the string. So I'm saying everything in that string up to not including minus 2, which will get rid of this extra plus sign right there. So that's why I put that in there. Okay, so that's good enough for me. I don't want to go into the details of making it better, but it is kind of a good exercise to try on your own to make it look exactly how you would write it typically. But this is fine for me. So now that we have a way of generating these strings, that we can put this into our class definition as a method. So this is what we did before, but now we're adding a new method called string. And it's the same exact code. So degree is equal to self now instead of p. So self referencing that instance. And then we start with an empty string, and then we slowly add on to that string, and then we return that string up to not including minus 2. So if we run this code, okay, let's see what it does. All right, so we're redefining our polynomial class. We create an instance, we print it, and then we print what it should look like, and then we print the string method that we just made. So this method. All right, not too bad. It's starting to look like what we want it to. However, I'm not necessarily satisfied with when I try to print p, this is what I get out, right? I get out this polynomial object text here. I would like it if I could just print p and it would automatically show the string representation. Well, this introduces another Dunder method called repr. So I've actually read before in the past that every class that you write should have a repr method. And the repr method is going to give this class a string representation. So basically all I did to change the code was in place of string, I wrote double underscore repr double underscore. So now if we run this code, we see that when we print p, right, we're just printing out p now. We're not calling any method. We're just printing p. This is what it looks like. And if you just type p in a cell below like this is what it returns. So this is one of these other double underscore methods that's used when you construct your own custom classes. And when you read other people's source code, you'll see this repr method all over the place. Okay, it's just a way of designing classes that are user-friendly. Okay, so next up, we probably want to evaluate a polynomial at a given instance of x, right? That's kind of the whole purpose of having these functions, is to evaluate them. So what we can do is add an evaluate method. So again, we reference ourselves, but now, in order to evaluate it at an x, we have to pass in something, right? So this method evaluate is going to take an argument x. Now, how are we going to do this? Well, I encourage you to look at this after class and kind of make sure that you understand what's happening. But it's really similar to the string method that we had, or the repr method. So in the string method, we slowly built up the coefficients in x to the appropriate power. In the evaluate method, we're going to, instead of having an empty string, we're going to start with a value of 0 and then increment that value by coefficient times x to the power degree minus I, and then return that value. All right, so let's go ahead and just copy all this code. So we're just redefining our polynomial, and then making another instance of P. So then, okay, we have the evaluate method, and notice right here, P.evaluate. Notice that we have to pass something in. If we did not pass in a number, we would get an error. Okay, so there's P there. And then here's P evaluated at 3 by calling this evaluate method. So hopefully this clears up when you need to pass in values into methods. And well, not when, but why sometimes you do and sometimes you don't. It just depends on the task at hand. Okay.
Professor, I have a question.
Yes.
So evaluate at 3, does it mean that it calculates the value of the polynomial at x equals 3?
Yes.
Okay.
Yes, exactly. Like for example, if I put in a 0 here, it's 1, as should be expected, because that's the polynomial. So next up, just as before, instead of calling a method, maybe we would want to just write something like this for a given instance P, right? And because Python is so vast, there's going to be a way to do this. And the way to do that is with the Dunder method call. So this is another double underscore method called call, and it will let us just pass in a value to a given instance of this class and have it do exactly what this evaluate method did. So all I did now to update my polynomial class is I replaced evaluate with double underscore call double underscore. So now I can just, actually I'll just do it right here just to show you. Just get rid of that. Double underscore call double underscore like that. And then instead of having to do this dot method, I can just do this. And you see that it works just fine. So it's another one of these magic methods that people talk about in Python. Again, there's a bunch of different ways to do this. There's a bunch of different Dunder methods to customize your class to do exactly what you want. For example, there's double underscore methods that allow you to add 2 different instances of a polynomial just by doing first instance plus another instance. Okay, so I just did that, and that will conclude my lecture on making custom classes. So I'm going to stop the recording here.